This next set of problems is going to deal with probability. So we're going to use some of the things that we learned before with counting, and we'll apply it to some of the probability problems. This probability problem is pretty straightforward. It's an example of just a simple probability. The tricky part about this is figuring out how many things have 4 legs. So let's go through the problem. Isabel has a farm play set that has 4 pigs, 3 horses, a cow, a snake, and a farmer. If she closes her eyes and randomly selects a figure to play with, what is the probability that the figure has 4 legs? So, to start off with, first we need to figure out how many figures we have, right? So how many figures are there? And so we can count. So there's 4 plus 3, 7, 8, 9, 10 figures total. Then we need to think about how many of those 10 figures has 4 legs. So I'm going to mark out the kind that don't have 4 legs. So the farmer, I'm presuming, does not have 4 legs, or the snake. So I've taken away 2 of the 10. So there are actually 8 figures in there. 4 pigs, 3 horses, so 4 plus 3 is 7, plus the cow, 8 4-legged creatures. So we have 8 out of 10. So 8 with 4 legs divided by 10 total number of figures. So this reduces down to 4/5. So the probability that Isabel draws a 4-legged creature from her selection is 4/5. This next probability problem has some of the same elements as the one we just did, in that we have to do a little bit of analysis of the situation and figure out what's actually being asked. We also have a new situation where we're looking at what happens after one event has already occurred. So an artist is making a mosaic and has several different types of tiles. In her bag, she has 100 squares, 25 rectangles, 50 triangles, 25 pentagons, and 1 decagon. She reaches in the bag and pulls out a pentagon. What is the probability that the next tile she randomly selects is a quadrilateral? So, one thing we need to think about is which of these different shapes are quadrilaterals. So I'm going to start there. And I will underline the shapes that are quadrilaterals, since that will be the focus of the probability that we're looking at. So squares are quadrilaterals. Remember, quadrilaterals are polygons with 4 sides. Okay, so squares have 4 sides, so a square is a quadrilateral. A rectangle has 4 sides, so a rectangle is a quadrilateral. Triangles only have 3 sides, so they're not quadrilaterals. Pentagons have 5 sides, they're not quadrilaterals. And decagons have 10 sides, so those are not quadrilaterals. So we have a total of 125 quadrilaterals in that bag. So 125 quadrilaterals in the bag. Okay. Now, as we try to find the probability of how many of pulling out a quadrilateral from the bag, we have to know how many shapes are in the bag. What's the total number of shapes in the bag? And so to do that, we're going to add up all of the number of shapes. So we have 100 squares, 25 rectangles, 50 triangles, 25 pentagons, and 1 decagon. So this is, what is that? 50 plus 50, 100, 201 shapes in the bag. Now here's where the problem's a little bit trickier, is she's already pulled out a pentagon. So the pentagon's gone. So in the scenario we're looking at, where we're being asked what is the probability of that the next tile she selects is a quadrilateral, we only have 200 shapes in the bag, okay, because that first pentagon was taken and it's out of the bag. So at this point, the probability is going to be 125 out of 200, because that's the number of shapes in the bag at this point. And this will reduce to, what? 25 will divide. Five-eighths. This next problem reads, there are 3 gold stars, 5 silver stars, and 12 bronze stars in a bag. If Lisa reaches in the bag and pulls out a star without looking, what is the probability that the star will not be silver? So this is a little bit different type of problem than we've had before, because we're asking about the probability that something doesn't happen. Now there's 2 ways of looking at this problem. We can turn it around and say, okay, so what's the probability that it will be bronze or gold? That's one way of thinking about it. So let's do that first. So one thing we need to know is how many total stars are in the bag. So there are 3 plus 5, 8 plus 12, so 20 stars in the bag. Now we need to ask ourselves, how many are not silver? Okay, so that would be the gold and the bronze stars. So there are 15 stars are not silver. Okay, so the probability of choosing a star that is not silver is going to be 15 divided by 20, which reduces to 3/4. So the probability that she pulls us at a star that is not silver is 3/4. Now, we could also solve this problem by looking at the probability that she pulls out a silver star and then subtracting that from 1, because these are complementary events. They both can't happen simultaneously. So another way to do this is to say, what's the probability that she draws a silver? And so the probability of a silver star coming out of that bag is, I don't want the blue, is 5 out of 20, which is 1/4. And if I subtract that from 1, that'll be the probability that she does not pull out a silver star. Rebecca is playing a game where one 6-sided die is rolled to determine how many spaces she advances on the board. What is the probability that she will advance at least 5 spaces? In this problem, we're assuming that it's a fair die, so that each face has an equally likely chance of being on top. And we need to pay careful attention to this language here. It's not asking what's the probability that she will advance 5 spaces. If that were the case, it would be 1 out of 6, because there's a probability of 1/6 that a 5 will be on the top face. But it's at least 5. So this is actually saying, what is the probability that she will, in fact, roll a 5 or a 6? All right, so there's 2 possibilities there out of equally likely events. So there's actually 2 out of 6, or the probability is 1/3 that she will roll at least a 5. If the spinner is spun twice, what is the probability it will land on the green square both times? This problem is a little bit more complicated than some of the others we've looked at, because we are looking at a series of events rather than just a single event. Okay, like rolling the die once or spinning the spinner once. We're doing this twice. And what happened before is a key part of what happens later when we put it all together. I think One of the easiest ways of looking at this is with a tree diagram. And there's a couple ways you can do the tree diagram. You can work out all the possibilities, or you can start out and say, here's the first spin. The probability that it's a green square, whoops, is 1/4. And that it's anything else, the probability is 3/4. Okay. Then, when we spin the spinner again, if we did green square the first time, we could have a green square again. And the probability of that green square is 1/4. And anything else is 3/4. And I could fill out the rest of this tree diagram, but I'm not going to, because what I'm really interested in is what happens if we have a green square spun and then another green square spun the second time. So really we're interested in this branch here of the tree. And so the probability that this is going to occur is 1/4 times 1/4, or 1/16. Now, there's another way of looking at this, and that is listing all of the possible outcomes. Okay, so we could have first, let's look at it this way. The total possible outcomes. For the first spin, there are 4 possibilities on the first spin, equally likely possibilities. On the second spin, there are also 4 equally likely possibilities. So there are a total of 16 possibilities in 2 spins. Then we want to look at how many ways can we get a green square each time in 2 spins? Well, there's one way on the first spin and one way on the second spin. So a total of 1 way to have a green square twice, a green square on 2 spins. So we have a probability of a green square both times of 1 out of 16. Kathy is playing Monopoly. She rolls 2 dice whose sum determines how many spaces she advances on the board. What is the probability she will move exactly 5 spaces? Now, this problem, I'm going to go into a little more detail than you would need strictly to solve the problem, because this idea of rolling 2 dice and looking at the sum and finding the probability of a particular sum coming up on the dice is a very common one. And so I want to just talk about general strategies for solving these types of problems. I think the easiest thing to do is to generate a chart, almost like an addition table, really, where we have the possibilities on one die, 1, 2, 3, 4, 5, 6, and the possibilities on the other die, 1, 2, 3, 4, 5, 6. This is going to give us a nice visual way of examining every possibility without getting cluttered up. Tree diagrams are nice when you've got small numbers of things to count or to look at, but when you've got larger numbers, making some kind of a chart or table is often going to be easier. So what I'm going to put now here in the chart, again, this is just like an addition table, is the sums of these numbers. So 1 plus 1, 2, 3, 4, 6, 7, 6, 7, 8. 7, 8, 9, 10, 11, 12. So what we can see here is that when we have two six-sided dice, we have 6 times 6, or 36 possible outcomes, which we could have figured out with our fancy counting before also. But here we can actually see all of those 36 outcomes. What this chart now tells us, though, is that we can look here and see how many ways are there to roll a 5. And so we can just count. Here's 1. I'll just circle them. 2, 3, 4 possible ways of rolling a 5. And you can see that, okay, we could roll a 1 on one die and a 4 on the other, a 2 on one, a 3 on the other, a 3 on the first die, a 2 on the second die, and a 4 on the first die, and a 1 on the second die. So we have a total of 4 out of 36 ways of moving exactly 5 spaces, and this reduces to 1/9. What's nice about a chart like this is once you've got it, you can start asking your students lots of different probability questions based on this chart. You know, questions like, what's the probability that she rolls a 7? Or what's the probability that she rolls a 12? You can also look at kind of trickier probabilities, things like, what's the probability that she rolls a 1 or a sum of 7? And can use that chart to investigate a large number of possible scenarios. A game involves shooting a free throw, then shooting a three-pointer. To win the game, you must make both shots. You make free throws 80% of the time, and you make three-pointers 40% of the time. What is the probability that you will win the game? Now, this is similar to the one the problem before where we were looking at what's the probability that we'll get a green square twice on the spinner. So the idea is we have to actually have both of these things occur in order to win the game. So what happens here is we look at it's 80% times, so that's the probability that we will make our free throw, and then multiply that with the probability that we are going to make the three-pointer. Okay, and this is going to happen 32% of the time. That feels bad. Like I'm just saying the answer.
Yeah, I was planning one of my slides.
Okay. Another way of looking at this is looking at the possible outcomes on a tree diagram. So the first possibility is that we're shooting the three-pointer. Oops, no, we're not. We're doing the free throw first. So here's our free throw. And that we make it, or make it, or miss. Okay, so there's an 80% chance that we're going to make our free throw, and a 20% chance that we miss it. Now, if we make the free throw, we then get the opportunity to do the three-pointer. And we can either make the three-pointer or miss it. The probability that we make the three-pointer is 40%. And the probability that we miss is 60%. Okay, so the key is we have to make both of these shots in order to win the game. So we have to figure out what's the probability of doing this and then also doing this three-point shot. And the probability is going to be 80% times 40%. Atlanta is playing Cleveland in the World Series. Each team has an even chance to win any given game. The World Series is won by the first team to win 4 games, so at most 7 games can be played. Atlanta is leading the series 3-2. What is the probability that Atlanta wins the series? All right, now this is a bit tricky because there are a couple of possibilities that can happen for Atlanta to win the series. One scenario is that Atlanta wins the next game, and then that's it. Series is over. They've won. The other possibility is that Atlanta loses the next game. So then Cleveland and Atlanta both have 3 games, and they have to go to that 7th game. And then Atlanta would then have to win that game in order to win the series. So let's draw out using a tree diagram. I think that's the easiest way to see this, the different possibilities for this scenario. So for the next game, we could have Atlanta wins or Cleveland wins. Okay, and each of those, we're told, has a probability of 1/2. So they have an even chance, which means the probability is 1/2. So if Atlanta wins, we're done. Okay, the series is over. So we don't need, there are no more branches on this part of the tree diagram. But if Cleveland wins, we have 2 possibilities. Either Atlanta wins or Cleveland wins. Again, with probability of 1/2. So what we're really interested in now is following the scenario where Atlanta wins. Okay, so there's 2 ways they could win. They could win this way by winning the first game, or they could win this way where Cleveland wins the next game and then Atlanta wins. Okay, so the probability here is 1/2. The probability here of this scenario is 1/2 times 1/2, which is 1/4. Okay, so the probability that Atlanta wins is going to be 1/2 plus 1/4, which is 3/4. Another way to look at this is to say, what's the probability that Cleveland wins? And then subtract that from 1, because that'll give us the probability that Atlanta wins. So we could look at this and say, all right, the probability that Cleveland wins is 1/2 to win the first game times 1/2 as they win the second game. So the probability that Cleveland wins is 1/4. And if we look at 1 minus 1/4, that gives us the probability that Atlanta wins, which is 3/4. So the same answer either way.